Hello, my name is Timo Vogt. I'm happy to do this presentation for Digitalize in Stockholm 2023. Our project is called Toward Accurate Surveillance of Mosquito Breeding Grounds using multispectral imagery and millimeter wave radar. This is joint work with researchers from University of Colombo in Sri Lanka and Markus Frier from KDH and my colleague Luca Motola at Rice and Uppsala University. So dengue fever is a mosquito-borne viral infection that affects lots of people all over the world. Interesting is also that the same mosquito spreads Zika, which is a very dangerous disease. And one of the things is that it may be possible that this virus actually will soon come to Europe. Also, it already now affects more than 40% of the world's population. So the goal of our project is that we want to detect breeding places with drones. So we want to, in the end, deploy a real-world system where we take aerial images from drones, visually map the breeding sites, and with this we can cover large areas. So in the first step, we want the drones to fly at higher altitude. There they should detect areas that need closer inspections and mark those areas in maps. In the second step, then we want to analyze the water areas. For this, we want to estimate the water depth and the larva density. We're using two different types of sensor for this. One is a millimeter wave radio, and also the second one are multispectral image sensors. So the first modality we use are millimeter wave radios. We use them to detect water and estimate the water depth. Here you can see the hardware setups. On the left side, you can see the sensor. In the middle, you can see a setup where we put the sensor quite high above some water buckets. And then on the right-hand side, you can see the drone equipped with the sensor. So first, we want to use the millimeter radio waves, the millimeter wave radios to identify water. In an initial lab experiment, we have shown that we receive different power levels for different materials. You can see in this graph that we get the highest received power level for water, which is closely followed by copper. In the next step, we are doing this with a sensor mounted on the drone. There we use average measurements because we have to reduce the impact of the vibrations from the drone. And what you can see in this graph here, that we can actually differentiate between water and ground. So these were the first experiments using millimeter wave radios. The other sensor modality that we're using is multispectral imagery. Typically, cameras only do RGB, red, green, and blue radio waves, light waves, but multispectral imagery also can detect has also other wave bands. Here you see the drone, and here you can see the image sensor that we are using. As mentioned, typical sensors have blue, green, and red, whereas the sensor that we're using has, besides those, also a wavelength for red edge and for near infrared. So one of the things we want to do also is here detect the water depth. And for this, we're using learning-based methods to detect and classify water. The idea is that when the water has a certain depth, you will not find any mosquitoes in this water. What we're using here is we're using a so-called faster region CNN, because that's very suitable for what we're doing, as we can process multispectral images efficiently, and we can also detect and classify water areas accurately. So one of the results that we're showing in this slide here you can see the very green nature of Sri Lanka, and here you can see that we're detecting water with a confidence of 69%, whereas here in this area we can detect water with high accuracy or with high confidence, here 98 and 95, whereas this area has a little bit of a lower detection confidence. So we've also used imagery to measure the water depth. We've worked very hard on trying to use signal processing before, but that has not worked out very well. It was very difficult. Now in this work, we also tried small-scale CNS. The intuition behind this is that signals are actually attenuated in water, and the reflected signal from the bottom can be picked up by our multispectral image sensors. For this, we have played with different CNN architectures. All of them had very few hidden layers, very few layers, 2 and 3, and we have used kernels of different sizes. To identify the architecture, we used these different models and computed the root mean square error and the R-square value. And it turned out that if you're using a larger set of pictures, we can actually get quite accurate results. So here we see in comparison the CNN model for different data sets that we collected. And you can see that we are actually doing quite well for all our data sets. The true value is actually or the predicted value is actually quite close to the true value, which means that we can quite accurately detect the water depth. In this experiment, we are also showing how many, what these additional wavelengths that our sensor actually help. So we can see when we're using all the 5 bands, we're getting kind of a low error and a high R-square value. And if we only use the original 3 colors that other sensors have, the error increases quite a lot. Using only one of these additional sensors does to some extent help, but it's still the best to use all of these 5 bands that our sensor offers. Here we can see that depending on the depth range, here we can see on the x-axis the depth range of the water, whereas in the y-axis we can see the error. And this again confirms that using the 5 bands, we can actually get the lowest errors. One thing that we are also working on currently is to actually classify water with and without larvae. So you can see that these are real-world experiments that we are doing. We are collecting buckets filled with water and filled with and without larvae. What we're doing then, we are placing a 20 × 20 pixel patch in the middle of the bucket and stacking the images of the 5 bands. And then we are moving this patch forward and backward along the x and the y-axis so that we get different pictures. In total, we have collected 370 images. We split them into 80% training and 20% testing. And the results we have achieved are actually quite promising, but here there is more work on the way. For example, what we also want to do, we want to show what kind of impact the density of the larvae has on how well we can detect them. So in summary, we're using different sensor modality to detect mosquito breeding size. We're using both millimeter radio wave and multispectral image sensors. What we have so far detected is that we can detect water, then we can detect the water depth, and we also can detect the mosquito larvae directly. One of our future goals is then to use these modalities to increase the accuracy so that we don't get too many false positives and detect all the larvae, which is necessary to fight the dengue fever. With this, I want to thank Digital Futures and VR for funding and all the project members for hard and great work, and also you for listening to this presentation. Thank you very much.